So welcome everyone to this actually last seminar of the series NEG-ROM. Today with us we have Yvon Maday, Professor Yvon Maday, and today he will talk about nonlinear compressive reduced basis approximation for PDEs. So please, Professor Maday, the stage is yours.
So I have a little problem because I don't see my mouse and I cannot.
Okay, we don't see your pointer actually.
Okay. What is it about here? Okay. Ah, voilà, c'est bon. Okay. Okay. So let me start. So I will present today a recent work that I have been working on, which is about nonlinear compressive reduced basis approximation for PDE, which is a joint work with Joshua Barnett and Charbel Farhat on one side, and Albert Cohen and Agustin Somakal on the other side. So let me remind you just a first presentation that you already know everything about reduced basis method, I guess. So typically reduced basis method propose an alternative approximated solution method for solving parameter-dependent differential equation, where the idea is to find a function u depending on a parameter p solution of a problem that can be time dependent and that I have written rapidly like this, okay? So the idea of the reduced basis method is to conceive the set of all or a large number of this solution when the parameter mu varies. So this solution depends maybe on space and time, or maybe on space only. And D is some, say, compact set of parameters. So the idea is that the set, the manifold U parameterized by the parameter mu has some feature. Okay, so this feature is related to the reducibility of the manifold S. And this is based generally on what we call the Kolmogorov N-width, which is the ability of S to be approximated by a linear n-dimensional subspace. So the idea is to introduce the deviation of S from a given set of dimension n xn, which is the E of S of xn in the first equation. And then what we look at is the Kolmogorov N-width, which is the best we can do by choosing adequately the space xn. So the dns of x is the infimum over all possible choice of vectorial space xn. Okay, so you know this very well. So when the Kolmogorov N-width is small, so you have an avenue of methods working in the basis set xn properly associated with the best fit. But when the Kolmogorov N-width is not small, what can we do? One method that we introduced with Nicolas Cagnard and Benjamin Stam in this paper is to try to better look at the set of all solutions. For instance, typically when you have a very small viscosity in a viscous Burger equation, the solution that is represented here in at different time steps, you see from a very regular sine wave will evolve like almost a step function that a priori has a very large Kolmogorov N-width. So what we can do is, if we center, if we, for instance, look at the inflection point and put all the inflection points of this curve at the same point, this is what we get. And then the solution look quite alike. And so gamma n is where I look at u of x minus gamma n, then you see that at different time, the solution looks quite similar and can indeed be represented by very few degrees of freedom, as is seen here on this POD analysis, where you see the red curve was the initial span of the eigenvalues if you start from this type of solution, and the green one is when you center the solution like this. So this is a way to understand, look typically, this is a kind of human intelligence that is used here in order to have a reduction of the complexity of the set of all solution, which is obtained simply by translating the solution and arrive to a smaller Kolmogorov n width. So then this can be seen because you see starting from a solution, you see the reconstruction in blue with 3 centered POD modes, and the red one has nothing to do with the solution. Okay, so you have a better convergence rate of the eigenvalues in a POD decomposition, and you have a better approximation property. So now, if you want to discretize this, what we proposed in that paper was to look at the scheme, finite difference scheme that we want to tackle. And what we say is that pourquoi ça passe pas là? Okay, you are still there? Okay. So this leads to, at each time, we consider UN, which is written at time tn, with a proper translation of the solution. And what we do is to try to discover what is the next translation gamma n plus 1 in a Galerkin way. And we try to minimize, qu'est-ce qui se passe? Voilà. We try to minimize over gamma n plus 1 and over the coefficient alpha n plus 1, so that the approximation of the solution un plus 1 will be written as, on the last line, the sum over I of alpha I n plus 1 phi I minus gamma n plus 1. So these are unknown, so that this is the closest to the right-hand side of the first equation, which is written more simply in the last line here. Okay? So this can be implemented, and this works. The problem is that this intelligence, human intelligence, can be difficult to extend to 2D and more. Okay? So if the Kolmogorov n width is not small, so what can we do? Okay, but the Kolmogorov n width is not everything here. Okay, so generally speaking, the process of dimensionality reduction can be described by a pair of continuous mapping. First, the encoder that goes from the Banach space in which the solution lives to Rm, and the decoder that goes from Rm to X, so that for every V in the solution space, the difference between V minus the decoder applied to the encoder applied to X is the smallest. Okay, so this is a formal way to propose dimensionality reduction. Okay. So now, if we optimize this by imposing some condition on the encoder and the decoder, we arrive to different possibilities. So if D and E are both assumed to be linear, of course, D composed with E is also linear, and then we arrive to the approximation number, which is obtained by the AM of S, which is the infimum over all linear map of the maximum of V in the solution space of V minus LV. So which is taken over all operators, linear operators of rank at most equal to M. So this is quite simple. Now, if only D is assumed to be linear and we leave E to be any, then we arrive to the Kolmogorov N-width that I spoke already. And obviously, because E in a larger set, the Kolmogorov width is smaller than the approximation number. Okay. Now let's complicate it still a little bit more. Now E is assumed to be linear and D is assumed to be nonlinear. And then we arrive to something which is the sensing number, which is the infimum over all D, which is nonlinear, and lambda 1, lambda 2, lambda n that are linear functionals, so that the maximum over all functions in the solution space of V minus D applied to the result of the lambda 1 of V, lambda 2 of V, lambda m of V is the smallest, okay? So then this, I have no time to explain much, can be related to the Gelfand width, Gelfand and width, that actually, in case S is convex and centrally symmetric, the last line is the relation that exists between the sensing number and the Gelfand M width, which is Sm is less than the dm of S minus S, and which is less than 2 times the sensing number of S. S minus S meaning all functions that are written as the subtraction of 2 elements in S. Okay, and now we arrive to the nonlinear width of manifold width, where E and D are any, and so not exactly any, because for stability purpose, we are interested in having Lipschitz condition on D and E, and this results gives the delta gamma M of S, which is referred to as the stable manifold width or stable nonlinear width. Okay, so now we have many ways to conceive the dimensions, the complexity of S, and you see that the Kolmogorov N width is not everything. Okay, so there are cases where, and we saw it, where the Kolmogorov N width may be very small, and this same set of solution may have a Gelfand width, sensing width that may be much, much smaller. Okay, so for instance, a basic example is the step function, which is the set of all these indicator function of the set A plus L between 0 and 1, where A belongs to 0, 1, and L is a positive number. Of course, it has some restriction, and we consider it in a periodic way. So we periodify this function. So we periodify it, and we remark that the parameter A and L are not are enough to express exactly the solution U. So U depends on these 2 parameters, A and L, that are not linear functionals of U. They can be easily recovered from U. For instance, we can propose 2 linear functionals, lambda 0 and lambda 1, which is the average and the momentum of U with respect to X. And you see that from this, we can obtain the value, recover the value of A and L, because lambda 0 is equal to L, and lambda 1 is 1/2 of L times 2A plus L. So A and L can be recovered exactly from the 2 averages that are linear functionals from U, okay, but they are not linear functionals of U themselves, because if L is equal to lambda 0, of course, A is lambda 1, 2 lambda 1 divided by L divided by 2 minus L, something like this, okay? So therefore, this means that the sensing dimension of N width of S is equal to 0 for every M larger than 2. Okay, so which is very convenient. So in this contribution, we will deal with situations where the Kolmogorov M width is with a slow decay, and the sensing number decays much faster. Okay, so how can we use this? Okay, so for a target accuracy, what we can say is that we will need a large number of POD function a la Kolmogorov in order to approximate with an accuracy of epsilon the solution. Nevertheless, with fewer information, we can non-linearly recompose the solution because Sn of S with the same accuracy as the n, which is much smaller. Okay. So, in order to proceed and to be computable, what we can do, what we propose to do, is to use the linear functionals that are the few first coefficients in a reduced basis, in a classical reduced or POD basis, and then recompose the other coefficient of the reduced basis from the first one. Okay, so what we do is to evaluate with a reduced basis Ej from j equal to 1 to capital N, with n quite large because due to the Kolmogorov in which we need a large number of these functions, these basis set, in order to approximate well the function u, but we say that the coefficients are not all independent, they are not all degrees of freedom, only the first one are degrees of freedom, the last one are not, and can be recovered from the first one. So how do we do this? We have to predict a value of lambda k of v, this lambda k of v that I will denote later like v at k, which are the coefficient in the reduced basis for k going from small n plus 1 to capital N being the Kolmogorov n with small n being the sensing number. We will approximate, we will learn the functional pk that from lambda 1 to lambda n of v is able to reconstruct lambda k of v. Okay, and then of course the problem will be of dimension small n and not capital N. Okay, so in order to understand how this can be done, we can define the pk in a class, in the rich enough class of function that is able to approximate well the solution lambda k from lambda 1, lambda n of ui being some snapshots you computed with some parameters value mu I. So we can consider the class of functions that are maybe quadratic functions, maybe that are polynomials of higher degree, or that are obtained with an artificial intelligent architecture, a neural network, for instance. Okay, so let us, in order to proceed pace by pace, step by step, let us consider a little modification of the step function, which is b times the step function from a to a plus l in a one periodic sense. And so first of all, what is the reduced basis associated to the set of all u mu's? It appears that the u mu is can be seen as a periodic stationary process, and then the Karhunen-Love basis is exactly the basis Fourier series of 0, 1. So let's simplify the analysis. For this set of function, when the a, the length of the step function L, and the value b of the step function when it is not equal to 0 varies, then this set of functions, when a, b, and l vary, actually can be represented well approximated in a Fourier series. This is the Karhunen-Love expansion. Okay, so due to this, we do the expansion of u mu in the Fourier basis, and because we are it is a real function, we prefer to use the cosine and the sine. The cosine with the coefficient alpha k and the sign with the coefficient beta k. So every u mu can be represented because it is a periodic function like a Fourier expansion, but the Fourier expansion is the best, the more condensed one, and we can compute the coefficient with alpha 0, which is BL, and alpha k and beta k for every k, which is given by the expression below, where you see that actually the coefficient behave like 1 over k, roughly speaking, because the sine and the cosine are mostly between 0 and 1 in absolute value, of course, and this coefficient behave like 1 over k. This is well known, and due to this, the Kolmogorov width of scales like m to the power 1 minus 1/2, which is well known. Okay, so due to this, the Kolmogorov width is not very, very rapid. And so we need a large number of Fourier coefficients in order to get a good approximation of u of nu. Okay, so now let us continue in the direction of trying to identify what are the linear forms, the Fourier coefficients that are able to represent well the function u of nu. And we remark that if we consider alpha 0, alpha 1, and beta 1, i.e. the two first coefficients of in the cosine and the first coefficient in the sine wave function, we can recover exactly the value A, the value B, and the value L, okay? The recovery map does not have an explicit form, but this set of three equations with three unknowns, which is nonlinear, has a solution, and we can express A, B, and L from alpha 0, alpha 1, and beta 1. So because of this, and let me go back to the form of alpha k and beta k as an expression of A, B, and L, you see that if I know A, B, and L from alpha 0, alpha 1, and beta 1, I know every coefficient alpha k, beta k, meaning that indeed the sensing dimension of k is less, for m equal to 3, is equal to 0, okay? So I can recover every coefficient, and due to this, I can try to learn what are the value of alpha k, beta k, if I know alpha 0, alpha 1, beta 1. And this is what I obtain here by taking f as being linear function, polynomial of degree 2, polynomial of degree 4, or using decision tree or random forest. So this is what I get if I use 2 coefficients, 3 coefficients, or 5 coefficients. You see that this is the mean square error because we are in a framework of a random process. And you see here that the linear regression, the degree 4 and the null have exactly the same approximation property, which is bad. Okay, so the good idea is not to use a polynomial representation even of degree 4. The good idea is to use a regression tree, a tree or a random forest in order to approximate this solution. So you see that with 1,000 training sample, this is the accuracy we get. If we go to 10,000 training sample, we get an accuracy of 10 to 10 minus 4, which is quite good in order to get the approximation. Now, this was if I consider the set for where are fixed the b equal to 1, and I set the length equal to 0.5, meaning that A is the only parameter. Now, if I go to only fixing L equal to 0.5 with 10,000 training samples, so where I have to recover A and B, you see here that with 10,000, I get an accuracy of 10 minus 3 with the tree or the random forest. which is pretty good. Okay, so now in the perspective of applying this to more complex situation, and where I expect to that my solution will be something which is rather regular, multiplied or plus a step function. It may not be in the first coefficient that I will have the information, but better in the larger coefficient, the one that will be associated to the discontinuity and not to the modulation. Okay. So the idea is to consider the question, to address the question, if we can recover all the coefficients from the one with a larger k. And what is obtained in the case where b and l are constant is that a can indeed be recovered by alpha k and beta k modulo 1 over k, meaning that if we use the same formula with k plus 1, we have a modulo 1 divided by k plus 1, which means that we can indeed now with these two equations recover exactly the value of a, because if a and a prime are equal modulo 1 over k and 1 over k plus 1, then belonging to 0, 1, there exists a unique solution, a equal to a prime to this. Meaning that we can recover from alpha k, beta k, alpha k plus 1, beta k plus 1, all the values of a, in case, again, L and B are fixed, and because we are able to recover a, we are able to recover all coefficients alpha L and beta L. This is what we show here, where from the coefficient k between 10 and 10 plus d, we are able to recover all the coefficients that are larger than this with the random forest. Okay, so in a nutshell, now let us explain how we will use this concept. Okay, so let us consider a simple problem. Find u solution of L of u plus J of u is equal to f, where the parameter has been hidden for the sake of simplicity. But there is a parameter here, and we want to approximate the solution with an expansion in a Karhumanov POD expansion. In the case where n bar is very large, and we are approximating u as a sum of u at k phi k. But we will separate the k into two sets. First, the k that are associated to degrees of freedom, so k going from 1 to n, the first n1, and the other one, n plus 1 to n bar, which is indexed by L, and where I will assume that the u at L, for L going from n plus 1 to n bar, can be well approximated by psi L, which is learned from u at 1, u at 2, u at n. Okay, so I learned this process in an offline stage, and then I propose an approximation u of n and n bar, which is the sum of the u at k phi k from k equal 1 to n, where the degrees of freedom are the u at k from k equal 1 to n, plus the complement of information, which is very, very important due to the Kolmogorov N which is large, but actually where the coefficients are expressed only from the degrees of freedom, k going from 1 to n, as we saw previously. Okay. So the idea is to plug this expression into a discretization scheme a la Galerkin, Fedot-Galerkin, whatever, that from the L curly U plus G curly U equal to F, using the approximation U and N bar, which is the sum with the degrees of freedom and the other part, which is expressed in terms of the degrees of freedom, into the equation that will be written like L applied to U and N bar plus G applied to U and N bar equal to 0. Okay, So here I separate the degrees of freedom from the other part, and what I can propose is to solve this iteratively, where because of the nonlinearity, it's quite natural to use this. I propose here only a Picard scheme, but of course, a more general nonlinear solver should be used, where U at k from k equal 1 to n will be obtained like a limit of ukp when p goes to infinity, and where u at p plus 1 is obtained by solving the last equation, where you see that I iterate, I put everything which is complicated in u in terms of the u at u at kp, and I discover the new value u at kp plus 1 from this equation. Okay, so what we have done is to use this on the 2D implicit Burger's equation, where there is a parameter mu1 and mu2 that is in the boundary condition and in the right-hand side, with this expression of x, the box between 0 and 100, y going between 1 and 100, the final time, which is 25, and the parameter that are in this range. This is done in collaboration with Joshua Barnett and Charbel Farhat. And so here, just to express that the solution has a kind of a discontinuity. So the Kolmogorov N width is very large, as can be seen with the decay of the singular values here. So what we get by implementing the nonlinear solver iterative that I proposed you is summarized here. So if we use a high order representation, it is 125,000 dimension based on 62,500 mesh point that run into 718 seconds. If we use a classical reduced order model, the dimension has to be large enough. Remember the decay of the coefficients here. So in order to have an accuracy of 10 minus 1, 10 minus 2, we need about 100 Kolmogorov dimensions. So here we use 95 degrees of freedom in order to represent well the solution. And we need mesh points in order to evaluate the nonlinearities, about 6,000 number of points, and we obtain in a walk clock time of 80, meaning a speed up factor of almost 9, we get an accuracy of 1.38. Now, if we use this nonlinear compressive reduced basis approximation based on only 10 degrees of freedom with something like 140 total number of Kolmogorov reduced basis, meaning that we have 130 coefficients in the reduced basis that are expressed like a function of only the 10 first coefficient. The walk clock time is reduced to 18.8 with a speed up factor of about 50, with almost the same accuracy, and based also on less number of points, because we used also here this possibility. We see here the solution with a classical reduced model or with the nonlinear compressive reduced basis on the right. And you see that we get less oscillation because we were able to have a larger number of Kolmogorov basis set on the right than on the left. Okay, so remember that we get a speed up factor for the right which is more than 50, meaning that by using more functions at la Kolmogorov, but with only 10 degrees of freedom, we do not reduce the accuracy, we improve the accuracy, we diminish the whole clock time, okay? So the approach proposed here is rooted on the classical model order reduction, so you don't have to modify everything. The only thing is that due to the fact that in some cases, the sensing number or the Gelfand and width allows to propose the fact that all the coefficients can be expressed like degrees of freedom and not all of them. So this learning phase actually is quite simple and reduced in size because, as I told you, we have 130 coefficients to learn with respect to 10 degrees of freedom, which means that this can be learned quite easily, actually more easily than in other founding approach where they use this type of neural network or deep autoencoder that require much more information. And due to the autoencoder, this was much more expensive. So this is just a preliminary rework, the analysis in 1D that we will continue with Albert Cohen and Agustin Somacal, and other numerical implementation that we will proceed with Charbel Farhat. So I thank you, and if you have questions, I will be happy to answer them.
Thank you very much, Professor Maday, for this talk. Now it's question time. So if you have questions, you can basically unmute yourself and you can ask directly to Professor Maday your question. So let me see if there are questions from the audience. Okay, so maybe I can break the ice with a question, actually.
Okay.
I mean, here in the last slide, actually, you are telling us that you are able to train the problem in a simpler way with respect to, autoencoder stuff that they proposed in model order reduction enhanced with the machine learning. Can you be a little bit more precise, like on training time with respect to other approaches, and also on how do you train if you tried several architectures, I don't know, something like that?
Okay, so I cannot be too much specific because I didn't do it myself, but the idea is that due to the fact that what you are learning is only the coefficients that are here, so you only need to learn. You are not learning a function, you are learning coefficient. So you are learning a mapping that goes from R10 to R to the 120, which means that it is very easy to learn this. Very easy means that we need quite a few numbers of snapshots in order to do this.
Okay, so the training should be quite faster, I mean, with respect to autoencoders or more complicated stuff.
Yes, so the offline stage.
Okay, and in the online
offline stage is
okay, and in the online stage, you still need to solve the problem. Like this is, you have the nonlinear equation and you solve iteratively the nonlinear equation. Am I right?
Exactly. Yeah. So with the as you see here, the nonlinear part. Is expressed in terms of the previous evaluation of the degrees of freedom, either appearing here directly or appearing here through the learning process.
Okay, so you don't have to reproject everything or use like hyperreduction or something like that. This is the reason.
No, we use hyperreduction, of course. The evaluation of G, requires an hyperreduction. Okay.
So you use both of them. Okay.
Yeah.
Okay.
Yeah. And this is what appears This is the size of the hyper-reduction.
Okay, great. I lost it. Okay.
62,500 is the number of mesh points. 6,000 is the number of mesh points that are used classically. It's not the empirical interpolation method, but it is a similar one.
Okay.
And it can be even reduced in case of this nonlinear compressing reduced basis approximation to 1,500.
Great. Thank you. Are there other questions for Professor Maday? Yes, Tommaso, I basically see that you are not.
Yeah. So,
Go ahead.
So, very nice talk. I have one curiosity. So on this slide, so if I understand correctly, this is a parametric case. So you're not trying to reproduce the result for the same value of mu1, mu2.
No.
Okay.
We are obtaining it for a different value of mu1 and mu2.
Okay. And my question is, did you try or do you envision to try to feed the neural network also with the value of the parameter?
We can, but so the idea is to be able to reconstruct a new solution which is not in the in the training set.
Yep. No, I see. But I'm trying to see because since it's a regression algorithm in a sense, the relation between let's say the first modes and the high frequency modes, the low frequency and the high frequency, you can try to also use the parameter as additional feature. But I mean, perhaps it's not worth it. But I was wondering if it's something that you tried or not. I'm saying that you're essentially, if I understand correctly, you're trying to build a map from the low frequency modes in a POD sense to the high frequency ones.
Yes, we try to learn this psi, okay?
Yeah.
That goes from the 10 first coefficient to the 130 frequencies. Okay.
Yeah, and I was trying to figure out if it could be worth it or why it's not worth it to essentially include as additional dependent variable the value of the parameter.
But attends, the value of the parameter is used. The value of the parameter is used. We use different parameters and different time step in order to learn this mapping. Okay. Okay, but it is a discrete one. It is a discrete set of parameters and a discrete set of snapshots.
I see. Okay.
Okay, so we learn this from preliminary computation, and we want to use this on another value of the parameter.
Yeah, no, okay. No, makes sense.
Okay.
Are there other questions for Professor Maday?
Sorry, can I ask a question? I'm sorry.
Of course, Ryan, go ahead.
Okay. So very nice talk, Yvonne. I really enjoyed it. Very new. My question is related maybe to something you said on the last slide. So did I understand correctly? So there is, theoretical support. So analysis for the method. Did I understand correctly?
For the moment, yes and no. What we are able to see is that indeed it is possible to recover from either beta k, alpha k, beta k plus 1, alpha k plus 1, everything that allows you to recover all the coefficients, okay? Or more simply, if you know alpha 0, alpha 1, and beta 1, you're able to recover everything also. Okay, so this is the theoretical part. Okay, what we prove is that what we see here is that the relation between A, B, and L and alpha 0, alpha 1, beta 1 is not a polynomial of degree 2. is not a polynomial, is much more complex, okay? So when you want to recover this mapping from a linear function for polynomial of degree 2 for polynomial of degree 4, of course, you will be able to improve a little bit the approximation, but you will not be able to hit it, okay? So what we have proven is that we need indeed either random forest or trees or whatever artificial intelligent algorithm that will be able to invert the mapping from ABL to some of the alpha and beta. What we were able also to see is that if we consider alpha 10, beta 10, alpha 11, beta 11, then the derivative of A with respect to these values is quite large, which means that we need, if we want to stabilize the mapping between A, L, and B and the beta K, alpha K, you will need a quite large number of these coefficients in order to be able to reconstruct A, B, and L, in order to reconstruct after all the coefficients, okay? So this is what is theoretically proven. Now, with artificial intelligence, already things that are proven that are not used here, and it might be interesting to show that indeed some special artificial intelligent algorithm will be able to properly learn and maybe give the type of sets that will be enough in order to secure the learning of the psyche. We have not done this.
Thank you. Impressive. Very nice. Thank you.
Hi, Yvon. It's great and entertaining talk as always. I just have a quick question right here. For the 10, you were saying the accuracy is better because 10 is like 140, right? The M bar.
Yes, I said that the classical ROM, so the accuracy is the same here, okay, because we use at the end, we use here about the same number of total Kolmogorov and width, even larger with okay. If we want to increase this, improve this, we will need to go to 1000, okay, because the Kolmogorov and width is like 1 over square root of m, okay? But already, so the accuracy here is decent, but you need a size of about 100 coefficients. We prove here that with only 10 degrees of freedom, we are able to recover about the same accuracy with, of course, a large speedup.
Could you just remind us how is M bar decided? So the other 130 is a function of the first 10, right? How is that total M bar decided?
But it is like always, when you look at this, if you want an accuracy of about this, you declare that you need 150 coefficient. If you want an accuracy which is smaller than 1%, you will need 300 coefficients. Okay, so N bar will be 300 if you want an accuracy of the order of 10 minus 3. If you want an accuracy of the order of 10 minus 4, you will need 700 coefficients. N bar will be 700, okay? Maybe N will be still 10 or 20, okay? We have not done this. It is something that we have to do, okay?
I see. So given N bar, how to locate N?
Yeah, but of course, if N bar is equal to 700, then it starts to be very, very accurate first, but also very expensive, because the number of reduced hyperreduction method that will be used here will give a very large number.
Thank you.
Are there other questions? Professor Yano, please.
Hi, Yvon. Very much enjoyed your talk. So I had one question on this example. So I understand that the dimension of the, I guess, the online space required to achieve given accuracy is lower because you're providing this additional compression for the, I guess, higher frequency modes. But does this also reduce the size of the training snapshot required to achieve given accuracy? So if we quantify the accuracy, not in terms of the size of the online system, but the size of the training set you need, does that also help in this, or does it not help too much because N bar is still large?
Alors, N bar is still large, but the learning is, as I said, to learn a map that go from R10 to R130. Okay, so which is pretty easy to do. Okay.
Right. Okay. But it still needs to be, I guess, large enough to generate that 140 linear radius spaces first. Is that, am I getting that correctly?
Yeah, yeah,
Okay.
absolutely, absolutely. You need to be able to construct, to build the 130 different mappings that are able to approximate accurately all the coefficients from 11 to 140.
Okay, okay, no, that makes sense. Okay, thank you.
You're welcome.
Let's see if there are other questions.
But each time you see, the problem you solve is this one, because all this part is going on the right-hand side.
Yes.
Right, right.
All this is going on the right-hand side, okay? And the only thing is to invert this part here, which is of dimension small n, 10 here.
Right. Yes. I think this makes sense. I was thinking of a scenario where, for example, for non-time dependent problems, just generating each snapshot can be quite expensive. So in that scenario, I guess there's not necessarily a significant reduction in the offline kind of a snapshot generation time.
Yeah, that's right. In the offline process, you have to understand in some sense the complexity of the problem.
Right.
You have to have a sense of this dimension. This can be greedy, okay, but at the end you will use exactly this. So you want to use exactly the same number of reduced basis. The reduced basis should be the same. We didn't use the same here. I don't know exactly when. I didn't do myself the computation. It would have been maybe wiser to use here to use here 140 also. So the idea is to compare a classical reduced model with 140 with this nonlinear compressing reduced basis based on 10 degrees of freedom and 130 other coefficient, so that it is equilibrated, and we get we get the same accuracy.
Right. So it's the kind of the additional compression that sits on top of the initial linear, I guess, the compression. Okay.
Exactly.
Makes sense. Yeah. Thank you.
You're welcome.
So it seems that there are no other questions. So I think that we can thank again Professor Maday for this very interesting talk. And I thank you all for this very nice discussion. And before leaving, actually, just an announcement. So this was the last talk of the series for this, let's say, spring edition. We will come back, actually, during the fall. So stay tuned. We will update you by mails. And also, we will keep update also the website. So thank you very much for staying with us. And I hope to see you all again during the fall edition, let's say. So thank you, Professor Maday. Thank you, all of you, for being with us. Thank you.
Thank you for organizing this. It was very nice to see you all around, and it's a long time I didn't see some of you, so it was very, very nice. Thank you. Thank you for being there, and thank you for organizing this event.
Thank you.